Nanochemistry is concerned with the study of particles, with an order of magnitude between 1 to 100 nanometers. But exactly how small is this? Well, about 1 million silver nanoparticles laid end-to-end would be just 5 centimeters in length. Nanochemistry will play a profound role in the future of medicine, such as nanosponges, which can remove toxins from the body. It will also form an integral part of environmental chemistry, such as lightweight carbon nanotubes, which can be used in wind turbine blades for more efficient power generation. As a component of our nanochemistry research, we synthesized silver nanoparticles and examined how the addition of bromide ions alter the optical properties of the silver nanoparticles. In order to do so, sodium citrate, silver nitrate, and hydrogen peroxide were added to a number of 22 ml vials. Different volumes of potassium bromide were added to each of the vials, ranging from 0 to 60 microliters. Finally, 2.5 ml of sodium borohydride was added to each of the vials. A redox reaction is activated upon the addition of sodium borohydride, where silver ions are reduced to its elemental form and begins to aggregate. Sodium citrate acts as a stabilizing agent, surrounding the nanoparticles with negatively charged citrate ions, thereby preventing the formation of bulk silver. However, as the nanoparticles are formed, hydrogen peroxide begins to etch the growing surface, oxidizing silver back into its ions at a slower rate. Bromide ions bind more strongly to silver cations to form silver bromide, thus arresting the growth of silver nanoparticles. The way we perceive color is in terms of the wavelengths of incident light, i.e. white light, that is not absorbed. For example, a solid that absorbs red light and reflects all the other colors will appear green, as it can be analyzed through Newton's wheel. The different sizes of nanoprisms appear as different colors due to surface plasmon resonance. Electrons in bulk silver are bound to the positive lattice. Visible light does not have enough energy to resonate with these electrons, so is reflected off the surface, thus giving bulk silver its metallic luster. However, silver nanoparticles interact differently with visible light. They have free electrons which oscillate about the nanoparticle in the presence of oscillating electric and magnetic fields. Electron clouds of different sized nanoparticles resonate with light of different wavelengths, thus resulting in the different colors. But how is the size of nanoprisms actually measured? One of the techniques used is dynamic light scattering, DLS, which measures the Brownian motion of suspended nanoparticles in order to calculate their hydrodynamic diameter. And here's what we found out. The addition of different volumes of potassium bromide yielded different colored solutions due to the absorbance of different wavelengths of visible light. DLS plots the intensity of the light scattered as a function of the diameter of the nanoparticles. Even though potassium bromide allows relatively precise control over the size of the nanoparticles, there is often a range of nanoprisms of different sizes in the colloid. Peaks in the DLS graph correspond to the size that the majority of nanoparticles lie in. The graph of the silver nanoparticle size, plotted against the volume of potassium bromide added, is counterintuitive to what we expected. We actually discovered that the hydrodynamic diameter increased upon the addition of bromide ions. It is clear that nanochemistry and its vast applications will play a pivotal role in the 21st century, and this research has only helped to kickstart our interest.